All right. So, chapter 2 is entitled Computer Codes. Now, this could be somewhat misleading because there are many different kinds of codes. So, here are the three main kinds of codes related to computers. And they're all very different in a sense. So, the first one, and probably that's the first one you think about when you hear code, is secret codes. And so, encryption. So the point of these codes is to mask information that you're trying to exchange with somebody, and you don't want people eavesdropping. You don't want people to read this information. It's secret. For example, if you are communicating with your bank, you don't want other people to know what you're doing with the bank, so you would like this information to be encrypted. So that's not the kind of codes we're going to be talking about. I will mention them once in a while if I have some time, because there's some very interesting stuff, obviously. The second kind of computer codes, which is very important, is error correcting codes and error detecting codes. We will see a little bit of this in the slides that I'm going to show you in a few minutes. But these are used everywhere. If you think of any material medium that uses a lot of information, think of CDs and DVDs. When you're reading a CD, when the machine is reading a CD or a DVD, there's a lot of bits being transferred, and there are errors that are going to creep up. And so the information is actually encoded to prevent errors from being transferred to your screen, basically, so you won't or your speakers. I will talk about this very briefly at some point, but again, this can get very technical. And finally, the last kind of code that we can think about when we're talking about machines is just straightforward encodings of information into the machine. That's the kind of code we want to look at here. And so this is mainly the codes that we're talking about in chapter 2. So let's share the slides right here. Here we go. Okay. So here we go. Chapter 2, computer codes. So today's lecture deals with BCD codes and ASCII. So what's BCD? So BCD stands for binary coded decimal. So we saw binary earlier a couple of weeks ago, and so you can write down numbers in binary, and that's one way that you could actually, if you want, write them into the computer. But there's an alternative to writing decimal numbers in a computer, which is the following. Okay, so rather than take a number and write it, just convert it to binary and write down the bits, what you do is you encode the digits, the decimal digits, one at a time. So let's see what I mean by this. Brandon, here we go. Okay, so the most basic method of doing this is called 8421 or 4-bit BCD code. Okay, if you look at that little table there, if you read it and you think about it just a few seconds, what you're seeing on the left are the decimal digits. And on the right, if you look at those 4 bits, it's just that decimal digit written in binary. That's all it is. Okay, so 0, 1, 2, 3, 4. That's it. Okay, so let's take an example. I mean, this is like super simple. You take the decimal number 749. Okay, if you encode it in BCD, 8421 BCD code, here's what you do. Okay, you're going to have 4 bits for each of the digits. Okay, So that's 3 blocks of 4 bits, okay? And each block will represent a digit. So 1 block for 7, 1 block for 4, 1 block for 9. Okay, so if you look up the table, or if you just, it's straightforward, right? You just take the decimal digit and you write it down in binary on 4 bits, and this is what you get, right? So if you look, this is 7 in binary, this is 4 in binary, and this is 9. Oops, this is 9. Oh, this is wonderful. Let's forget about that cursor there. So this is 9 in binary, right? So you're just basically taking, rather than writing 749 in binary, you write each digit, decimal digit in binary, okay? So super straightforward. There's nothing deep about this. Question is, why do we want to do that? Okay? So the reason is humans work in base 10. Okay, so that's the natural base for us, and so there are advantages of encoding the decimal numbers in this way in the machine. Okay, first of all, scaling by a factor of 10, which is something that we do quite a bit, right? So you multiply by 10, you divide by 10. So in decimal, all that does is you move the decimal point, right? If you try to do that when you write your numbers in binary, it doesn't work that way, right? You can multiply by 2 easily, but multiplying by 10 is going to jumble up all the bits, right? But if you write it in BCD, you're encoding the digits. So let's say multiplying by 10, all you have to do is just add 4 new bits with all zeros, right? That's all you have to do. It's very simple. Okay. Rounding in the decimal number is very easy, right? For the same reason, okay? This is something I didn't talk about very much, but if you try the exercises, if you're converting certain decimal fractions to binary, you will encounter non-terminating binary fractions which are terminating in decimal. So what do I mean by non-terminating? I mean, think of 1/3 in decimal is 0.333333, never stops, right? Well, in binary, you have fractions which are terminating in decimal but non-terminating in binary. I'm not sure I've assigned a problem like that in the book, but there might have been one, okay? So this, if you're using BCD, it eliminates this problem, okay? And last but not least is conversion to character form. For example, ASCII, which I'll talk about in just a sec, is very easy. So what do I mean is, so imagine that the machine is doing a computation, and at the end it has to write the answer on the screen. So if it's in binary, it'll have to do some sort of computation to look up the code for the character, which corresponds to the number, okay? But if you're using BCD, it's straightforward. You just have it directly, okay? And you will see that in a few minutes, okay? Disadvantages. Well, there has to be some disadvantage. There are 2 main disadvantages. The most obvious one is arithmetic operations. They're not as nice to implement. The circuitry is more complicated because you're not doing straight binary, but it's some sort of hybrid encoding. You lose memory space. Why is that? Because on each of the 4 bits that you're using for a single character, there are codes that you are not using, which are 1010 right up to 1111, right? Because the digit you have, because on 4 bits, you can encode 16 different things, but now you're using 4 bits only to encode the digits 0 to 9, that's 10. So it's not efficient from a memory point of view, okay? We're not going to look at packed BCDs, by the way, okay? All right, so what's 6-bit? Okay, by the way, what I've just said is about the deepest thing I'm going to talk about today. So, All right. Okay. So if you see what I'm talking about, the rest is just basically just very simple terminology. Okay. So, all right. So what are 6-bit and 7-bit BCD codes? Okay. Um, it's the same thing. Okay. So you have, let's say 6 bits. Okay. So you have 4 bits, as you saw in the little picture there. If you, the first bits on the right are the numeric bits, which are used exactly like we did earlier. And you have 2 extra bits, which are called zone bits. And that allows you to encode more stuff, right? So let's say you want to encode letters, alphabetic characters. You can encode the digits, special characters, plus, minus, product, and so forth and so on. Okay, so you have these 2 extra bits to encode more stuff. Okay, and so one standard way of encoding the digits is to put them in zone 0, 0. So if the first 2 bits, zone bits, are 0, 0, then this tells the machine that what follows is the code for a digit. Okay, that's very standard. Okay, the 7th bit, this is kind of cute. So here's our first error detecting code. It's the simplest one that you can think of. It's called a parity check bit. Okay, so I have my 4 numeric bits. I have 2 zone bits, so basically just 6 bits that encode some kind of information. And there's a 7th bit, which is the parity check bit, which is there only to see that the code that's being transmitted or kept in memory is error-free to some extent. Okay, so errors can creep up when you're transmitting, when you're copying down information when it's being transmitted. Okay, so, and of course inside the machine there's transmission of information all over the place. So this is extremely useful to see if there has been some error. Okay, so how does it work? Okay, um, so this allows you to detect if 1 bit has messed up. Okay, so here is the first way to do this. It's called odd parity. There's odd parity or even parity. It's the same principle. It's exactly the same thing. Okay, but let's just illustrate with odd parity. So let's say that I have a code which is 000111. So that's a 6-bit BCD code, okay, which would probably stand for the character or the number 7 because the zone bits are 00. So this stands for 7, okay? So if you add up the bits of these 6, you look at these 6 bits, you add them up, you get 3, okay? This is odd. So you're going to set the parity bit to 0. So what you want is to keep the total sum of bits odd, okay? So then the 7-bit BCD code that you're going to store in memory will be the code you had, the BCD code you had, and you add a 0 at the start, okay? So you see that everything adds up to an odd number, okay? So now let's say that you have a different 6-bit BCD code, which is 001001. You look at the first 2 bits, there's 0, that's the zone bits. So you're guessing that what follows is a digit, and that's 9 in binary, so that would be the digit 9. Okay, but in any case, if you add those bits up, you get 2. This is even, but you want always to have odd parity. Okay, so you set the parity bit to 1, so the whole thing adds up to 3 and it's odd, so that's correct. Okay, so that's an encoding, if you wish, so that we have 6 bits that encode something, and then we add a 7th bit just to check that the parity is as we want it to be. Okay, so how is this used? So suppose that one part of the machine receives some data, okay? And so here's some data that it receives, and you look at these sequences of bits. There are 7. it's known in the machine that these are 7-bit BCD codes. So the first bit is a parity check bit, okay? So you look at the first sequence here, and you get 1011101 that adds up to 5. That's odd, no problem. Second one also adds up to 5. Everything is fine. And the third one, if you add up the bits, they add up to 4. And so the machine immediately detects that there's an error, okay? So there has to be an error in this third sequence. So what does the machine do? It asks for the sequence again, okay? Hopefully it'll get the right one after that, okay? Now, if you think about it, I mean, the quickest of you or those who are, anyway, you may have figured that, wait a minute, I mean, what happens if there are 2 errors in there? Yeah, so if there are 2 errors, this is not going to work. If you flip 2 bits, then this is not going to do the job, okay? But that's another story. Okay. Even parity is exactly the same trick, except that rather than keeping the sum odd, you keep it even. So it's just the reverse, okay? But it's as long as obviously the machine knows what's the right one, then it's the same thing, right? Okay, so these are error detecting codes, okay? There are codes which can actually correct errors, okay? So, which is quite remarkable because you don't have to ask for retransmission. The machine gets a code, it checks, it says, oh, there's a mistake, so let's correct the mistake and let's keep on going. Now, you might wonder, how can you do something like that? So let me show you very briefly. I've got to do this. I've got to do that. Okay, I mean, this is a very, very simple-minded error correcting code, but you'll see the idea, okay? So this is outside the scope of the course, by the way. It's just a simple error correcting code. Okay, so suppose that you send out a probe into space and it's sending back information, and it's like millions of kilometers away. So sending information back and forth is very long. So you'd rather be able to correct the errors rather than say, oh, there's a mistake. Let's send something back to the probe and then wait for it to send something back. That's going to take a very, very long time. So here's a trick. So suppose that your probe sends the following sequence of bits: 0, 1, 0, 0, 1. So of course it's sending out millions and millions of these bits, right? But there's cosmic rays, there's all sorts of things that can go wrong. It's really far, so I mean, these bits could flip and you'll never know, right? So what you do instead is, or wants to send, okay? So actually we'll send this. So here, I mean, this is a very simple-minded trick, but you'll see. So rather than send 0, send it 5 times. If rather than send 1, send it 5 times. I mean, this is like the stupidest error correcting code, but it works. It's just not very efficient. You can make this more efficient, but it's trickier. Okay, so let's say this is what the probe sends. Okay, and suppose that there's some noise and we receive this. So I'm going to, let's say, receive this. So this is what the information we receive from the probe, okay? So let's look at the first, whoops, I've got one too many in there, sorry. Okay, so suppose this is what we receive from the probe. So you see the trick, right? So
you have one too many in the second to last digit as well.
Yes, thank you. Getting excited here. Here we go. Wow, what the hell? Like that. Okay. All right, so this is what we receive from the probe. So I look at the first sequence here. I mean, what's very likely that the probe sent? I mean, all zeros, right? So likely sent is all zeros. What's the likeliest sequence that was sent here? It's all ones, right? And here it's a bit trickier, but I mean, with good probability, it's all zeros, right? Unless there are actually 3 errors, I mean, this will be all zeros. You see, it's trickier, right? But of course, if a lot of bits go wrong, then it's not going to work. You're going to get an error. But with a high probability, you're going to be able to actually correct all the errors just by doing this, which is quite smart, right? So we've corrected the errors. Right? So that's like the simplest example I can give you, that a code actually can help to correct the errors, even though we don't know what was sent, right? So of course the trick is, so this is not super efficient. And of course, if the probability that bits flip is rather high, then 5 bits is not going to cut it. So you'd have to maybe send each bit 100 times, but you see that's very inefficient. So the trick is to find codes that are more compact, but are still resistant to some probability of error, right? So there's a lot of research being done on these things. So I just wanted to show you the simplest possible kind of error correcting codes. Okay, let's go back to our slides. We are here. Oh boy. Okay, yeah, almost everybody's here. That's good. Oh, sorry. Okay, so this is done. Okay, 8-bit BCD codes. Okay, so this is the same trick as the 6-bit BCD code, except that rather than having just 2 zone bits, you have 4 zone bits. So you have more space to encode things, okay? An example of an 8-bit BCD code is ASCII, American Standard Code for Information Interchange. So this is a standard, and which has exactly this shape. It's 4 zone bits, 4 numeric bits. Okay, where do you find the digits in ASCII? In zone 0011. Okay, so it means that the first 4 bits, when they are 0011, you know that the next 4 bits encode the digits 0 to 9. Okay, now if you write this in hex, you remember, right? So binary and hex are very, very closely related, right? So you, in hex, what you do, if you have a sequence of bits, each group of 4 bits, starting on the right, is 1 hex digit. So the ASCII codes for the digits 0 to 9 are very easy to write down in hex. It's 30 right up to 39. You see that the digit appears naturally as the second digit, the hex digit. Okay. So now this is important. Everybody pay attention. In the book, the ASCII table, which is in the book, is obsolete. It is incorrect. It's no good anymore. Okay. It's no good, obsolete. So the table in the book is no good. Okay. All right. This is a correct ASCII chart. I'll share it on Leia.
Sir,
Yep.
what are we supposed to see on our screens
we don't
right
see
now?
anything.
You don't see the, oh man.
We still see the simple error correcting code.
Oh,
we still see CC.
okay. All right. Damn. Okay, let's do that.
So whatever you just said, I was like confused.
Yeah, okay, let's do that again. I had a feeling, but nobody was saying anything, so I thought, okay, this should be
Well,
okay.
I didn't we didn't see you like write anything or like hear you write anything, so we're like,
Yeah.
are you still like on the same table or like on the same?
Okay, I'm on. Can you see the slides?
Yeah, now we can see it.
You can see. All right, so that's what that's what I was doing. Okay, let's rewind. Let's do it again. 8-bit BCD codes. Same thing as 6-bit BCD code, except 4 zone bits rather than 2. Okay, so you can encode more stuff. Oh, what is going on? Okay. ASCII. ASCII is an example of an 8-bit BCD code. ASCII stands for American Standard Code for Information Interchange. Okay, so it is a way of encoding characters. Okay, so it has 4 zone bits and 4 numeric bits. I have a chat here somewhere. Somebody wrote, yeah, okay, all right, good. Okay, so to repeat, so the digits are found in zone 3, 0011, okay? So if you look at the codes 0011 with all zeros, that's 0, 0011 with 0001, that's the ASCII code for 1, and so on right up to 9, okay? Now, as I said, if you write down an 8-bit sequence, right? A binary number with 8 bits, you can write it in hex with 2 hex digits, right? Because you have a hex digit for each 4 bits. So these ASCII codes for the characters 0 to 9 are easy to write down in hex. It's 30 right through 39, right? So this is 3 in hex. This is 0. So that's 30 in hex, okay? All right. Now, I repeat, the ASCII table in the book is obsolete, no good anymore, okay? All right. This is a correct ASCII chart, which will be available for tests and such. How do you read this? So you look at the left-hand column and you have numbers from 0 to 7. So that basically here, this is a shortened ASCII chart. You have the zone bit. The zone bits have been chopped off to only 3 so that the table is a bit smaller here. So these are the zone bits right here. Can you see my cursor move?
Yeah,
okay.
it's just I'm really still confused. Like I really don't understand.
Okay. Where, when, take me where you
Like just like go back a slide earlier.
Okay. This?
Yeah, this right here. Like whenever you said like the in 4 zone bits.
Okay.
Right until there, I didn't understand.
Okay, you mean after that or before
Yeah,
that?
no, right after that, I didn't understand.
Okay.
So
So
the ASCII code, like how.
okay, so let me go to the table and show you, and maybe that'll clear that up. Okay, so we'll see the. So okay, so this table contains the. So these are the zone bits. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. It could go right up to 15, right, or F if in hex, but let's just keep it from 0 to 7. The top here are your numerical bits, the next 4 bits, okay? So what's inside the table is the ASCII code corresponding, okay, so the character that corresponds to the ASCII code. So let's forget about these old control characters. Don't worry about those, okay? We're only interested in the alpha numeric characters, which are over here. These are the guys we're interested in. So let's try to find the digits. They are here. right? These are the digits. So what's the ASCII code? It's 3, 0. Okay, ASCII code for 1 is 3, 1. Okay, maybe I need to write stuff. Let's try this. Okay.
So the left-hand column, it's the hex code, right? From 0 to 15, or like whatever.
Yeah.
And then on the top, it's all the numerical orders, but
yeah, let
same
me
thing,
just...
same thing. Is it not the same thing? Okay.
Yeah, because they're 8 bits, right? Okay, let's
No,
start.
I understand that.
Okay, let's try this. Okay, so here we go. I have my table like this. I have 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 9, 10, 11. This is in hex, right? D, E, F. So I look at, let's say, 4, 2. I'll have to look that up. What is 4, 2? That's the letter B, capital B. Okay, so this is capital B. Okay, so it means that the ASCII code for capital B is in hex, it is 42. Okay, so what that means, if you write it in binary, right? So this is 0, 0, 1, 0. This is 0, 1, 0, 0. Right? Hex is just shorthand for humans. It's binary for humans, right? So the ASCII code for the character capital B is 0100 0010. Do you see now how this works?
So you pretty much change all, like, so pretty much all binary codes goes into hex, and then you could use the all hex for the ASCII code.
Yeah. So hex binary is sort of the same thing,
Well,
right?
yeah,
It's just for us, it's easier to write, because if you start writing down 8 bits in binary, it's a mess, right?
Okay.
So hex is just for us an easier way to write down binary. Okay.
And is there a reason for us to go to the ASCII code, or? Like,
It's a standard that's used in all machines. I'll explain, but it's part of a bigger standard, but it's built in all machines, right? So it's really, yeah, it's a standard. You're not supposed to know it by heart, by the way. It's just to know how it works, right? So let's go back to the slides. Here we go. Can you see the slides? Yeah.
Yep.
All right. Okay. So here's our chart. I don't have an example, do I? Yes. Okay. So again, if you look at this chart, you have some control characters, which are essentially obsolete. We have some standard, characters like parentheses and plus and things like that. You have the digits, which are in the natural place, right? So you look at the 4 bits that correspond to the number. That's very useful because you can extract from, so let's say somebody types on their computer the digit 7, right? So the ASCII code goes into memory. You can read off the actual binary value of that digit directly, right? So if somebody types 6, so you have 8 bits, those last 4 bits are 6 in binary, right? So that's the idea of BCD code.
But I have a question for you.
Yep.
So whenever example, because now that's like not an oversimplified, but that's not the whole chart, is it?
Mm-hmm.
What would be under like 7, like going down?
After that,
yeah,
all sorts of different characters,
okay.
Which is not the nature of is not relevant.
So and the top from like where it says 00, is that all, like, is there like any obsolete in that chart, or is that the whole new chart?
No, okay. So the ASCII chart you see here is correct. That's the standard one. But
okay,
now it's part of
0.
Okay, yeah. But now it's all part of a much bigger standard, which I'm about to talk about Yeah, about to
Okay,
talk about. Yeah.
I just wanted to be sure there was no like obsolete part.
No. Everything there is
Because I
fine.
was getting confused. Okay.
Okay. All right. So yeah. So if you look at this chart, you see that there's a lot of standard characters which are not used, right? So for example, accents. There's nothing with an accent. What I'm going to add now is just to give you a frame of reference, but there's no exercises related to that from this point on. Okay. But again, so if you want to have accented characters or characters from different languages, you need a much larger code set, right? For many years, and still they're around, there's all sorts of different code sets. There's Latin 1, Windows 1252, ISO 88591, blah, blah, blah. And it causes a lot of problems. I mean, when I get my class lists, if you have an accent in your name and I take my class list and I bring it to this software rather than this software, then I get these junk characters that appear. So it's still, I mean, there's still problems with this, okay? But there is like a system to, sorry, I can't, wonderful. Okay, UTF-8 is a sort of universal character code set which supersedes everything, which is what should be or is being used. It does contain ASCII exactly with the same codes. Okay, so then the ASCII table that I've shown is just a small part of this big set. Okay. So all the information I'm going to give you now, you don't need to know. I'm just going to show you that there are variants and things and that. So it has variable with character encoding. It can use from 1 right up to 4 8-bit bytes, yeah, codes. So it's capable of encoding over 1 million valid symbols, which are defined by the Unicode standard. Okay, this goes back to 1992-93. It's due to Ken Thompson and Rob Pike. I don't know much about these things, by the way. It's just these are standards which are useful when you're using them. Yeah, so you might need several. Yeah, I don't think I've ever mentioned this, but a byte is 8 bits, but okay. You might need more than one sequence of 8 bits for a single character. Okay. Control or follow-up byte indicates that the following byte is still part of the current. Yeah, so it's built in that when the machine is reading these codes, it knows, oh, okay, so there's these 8 bits, but the next 8 bits are also part of the same character, so there's no confusion. Again, you don't need to know these things. Okay, this is just for reference, and I think that's pretty much it. Okay, so if you look at the exercises, it deals with BCD, 4-bit BCD codes, 6-bit, 7-bit, ASCII, and that's pretty much it. Okay, parity bit. It's really simple. It's very straightforward. Okay, so don't worry about this part. It's really it's not hard. So again, that last slide that I've shown you is just to give you an overview of what's being used right now, but you don't need to know these things. There are no exercises on this. Okay. Are there any questions up to this point? No questions. Okay, all right. So you have a WebWorks due this evening. I will let you work on that. I will maybe break you up in little rooms. Some of you have already finished, which is good. Some of you have not started yet. This is not so good. So I strongly urge you to do the problems. It's not hard. It's easy. And there are not that many. So please do.
Wait, sir, are you talking about the addition and subtraction of the?
Yep.
Okay. Yeah, it finished.
Okay.